2 moles of ideal helium gas are in rubber balloon at 30 degrees Celsius. The balloon is fully expandable and can be assumed to require no energy in its expansion. The temperature of the gas in the balloon is slowly changed to 35 degrees Celsius. The amount of heat required in raising the temperature is nearly, in joules, 62, 104, 124, 208. Take R as 8.31 joule per mole Kelvin. So we have a ideal helium gas, so ideal gas equation applies. We have got 2 moles, N equals 2. Helium is there, monoatomic gas. Okay, initial temperature is 30 degrees Celsius. The balloon is fully expandable and can be assumed to have to require no energy in its expansion. The temperature of the gas in the balloon is slowly changed to 35 degrees Celsius. So T2 is 35. Okay. The amount of heat required in raising the temperature is clearly okay. So we want to determine Q and we are given R. Okay, we want to determine Q and we are given R as 8.31 joule per mole Kelvin. Okay. Now let us focus our attention to the second statement in the problem. They're saying the balloon is fully expandable and can be assumed to require no energy in its expansion. Okay, see, look, the volume of the balloon is definitely going to increase, right? The volume of the balloon is increasing. Okay. Okay. But we take it as volume of gas increases. Okay, because expansion of balloon does not require any energy. It's only the increase in the volume of the gas, right? Okay. It's fully expandable. It is fully expandable. Now we need to correctly interpret these words. Okay, fully expandable means what? Fully expandable refers to expansion taking place at constant pressure. Okay, it is fully expandable. You can imagine the gradual increase in the volume of the balloon. Okay, and they're also saying the balloon, okay, there is a word where they say it slowly. Okay, the temperature of the gas in the balloon is slowly increased to 35 degrees Celsius. Okay, the temperature in the balloon is slowly changed to 35 degrees Celsius. That means it is definitely not an adiabatic process. Okay, it is, well, of course it is isothermal. Okay, sorry, it's not adiabatic, not also isothermal. It's not adiabatic because heat is being supplied. Okay, and it is also not isothermal because what? Look, it's not isothermal because temperature is changing. Also, we can also argue like this. First, not adiabatic as Q is non-zero. Number two, not isothermal, this process, not isothermal as delta T is not equal to 0. And it is also not isochoric as delta V is not equal to 0. Now because we have no other information, okay, no other specific kind of process, we can conclude that it has to be isobaric. Okay, and the second statement there is in full support of what we have concluded. Okay, so we can If not these three, then it has to be isobaric. Okay. Okay, so pressure is, otherwise they should give us the process in which, I mean, how the heat is supplied. Okay, so pressure is constant. Have you understood this?
Yes, sir.
Okay. Now, we have N. Okay. Okay, wait. We have to determine the heat, right? Okay. Let us first calculate CV and then CP. So what is CV? It is ideal monoatomic gas, right? So CV has to be the derivative of 3 by 2 RT per mole we are now calculating. So that has to be 3R by 2. Monoatomic implies Cp is equal to 5R by 2, and therefore heat supplied Q will be NCP delta T. N is 2, correct. N is 2. Cp is 5 into R is 8.31 by 2, and how much is delta T? 5 Kelvin or degree Celsius, doesn't matter. Okay, so 2 gets cancelled. 25 into 8.31, 25 into 8 is 200, right? And it's slightly greater than that, a third of 25. That is around, well, not third, sorry, into 3 by 10. So have some option comparable to that. 62, no. Yes, 208 is there. All other options are less than that. Okay, all other options are less than that, and therefore it should be 208. You can calculate it here also. But well, as far as the exam is concerned, you can just mark whatever option that was, D, I think, and skip, okay, and go for the next one. Yes, so it's 207.75 joules, which can be approximated to 208 joules, hence option D. Okay, did you understand? Yeah. Well, what I find is balloon is fully expandable and can be assumed to require no energy in its expansion. It's a bit difficult to arrive at the conclusion that the expansion takes place at constant pressure. But then you can ask yourself this question, like what are the processes that we have studied? And unless and until we have a specific equation for that process, okay, well, in mechanical engineering, we used to have a subject called thermodynamics, and there we would be having, or we would be given processes like this, where well, so this is usually called a polytropic process. Okay, where the value of n would vary. But because all of that is not there for us now, we ask ourselves, oh, what kind of process is it? It is not. It's not adiabatic because heat is required. That's what the question is saying. It's not adiabatic. It's not isothermal because heat is being, temperature is changing. Okay. It's also not isochoric because the balloon is expanding. Okay. So it has to be isobaric. Okay. So we consider Cp, heat supplied at constant pressure. Have you understood this? Yes. Okay.